Today's lesson is going to be about parent functions and some of their characteristics. When I'm saying parent functions, what I mean is just the simplest form of each type of function. For example, as you can see here on the screen, the first function I want to talk about is a linear function. A linear function, or the simplest version of a linear function, would simply just be f of x equals x, meaning what makes a function a linear function is when you have x to the first as the degree, meaning the highest exponent. So rather than have, a different y-intercept like plus 2 or minus 3 or something like that, or have a crazy slope of 3 over 7 or something like that, we'll just keep the slope at a simple positive 1, keep our y-intercept at a simple 0, and so it's just f of x equals x, or y equals x. Since that's the simplest version of a linear function, that would be the parent function. So first, as you can probably guess with the graph I've got here, the first thing I want to talk about is what the shape of that graph looks like. Well, if it's a linear function, it's got a slope of 1 over 1, y-intercept of 0. So that would mean we can put a point at 0, 0. And then we just would basically have this positively slanted line that would look something close to that. Not perfectly straight, but it's pretty close. Because it's just a slope of 1 over 1, right? So every time we're just going up 1 over 1. If you wanted to do an xy table to show that, remember the idea of an xy table is any equation, any function you are given can be graphed using this, where you just get to pick your own x value, plug it into the equation, see what you get for a y value. So like the reason I know 0, 0 is a point is if I plug in 0 for x, I would just get 0 because there's nothing else in that equation. Whatever you plug in for x is the answer you get out for y. If I plug in 1, I get 1. If I plug in negative 1, I get negative 1, right? So on and so forth. So that's your graph. Pretty simple, straight line, like we've come to expect from linear functions. The other thing I want to talk about is now looking at this graph, I want to determine the domain and the range for it. Now, if you have not already watched the video on domain and range, I would recommend going back and watching that, or making sure you are comfortable finding the domain and range of a graph, because otherwise this may not make sense. Domain is the x's, so x-axis is side to side, meaning for the domain we are interested in how far left the graph is going and how far right the graph is going. Well, looking at this, I pretty quickly see that one of our arrows here is pointing left forever, meaning it goes left forever to negative infinity, and one of our arrows is pointing right forever, so that'd be going to positive infinity. Notice both of them have parentheses because we only use parentheses with infinities. When I go for the range is the y's, the outputs. Y-axis is up and down, so I want to know how low the graph goes and how high the graph goes. Well, I have an arrow pointing down at the same time as it's pointing left, so I have to assume it's going to keep going down as well as left forever, meaning negative infinity. And my other arrow is pointing right and up, so I have to assume it's going to continue going up forever, meaning positive infinity. So our domain and range are actually the same with this graph, and not extremely tough to figure out. The nice thing with linear functions is, if you know much about linear functions, you know they are continuous lines that go forever. So your domain and range can pretty much be guaranteed for every linear function you would have. There's not going to be a whole lot of different stuff, no matter what type of transformations or translations you might have. Now let's take a look at the absolute value function. So if our parent function for a linear was just f of x equals x, then for absolute value function, really all we need to do is take that and make it an absolute value function, which, as the name would imply, means I want to take the absolute value of x. That's our parent function. Remember, absolute value is a measure of the distance a number is from 0. Distances are always positive, and so absolute value will always give you positive numbers. So if I was to do an xy table for this equation, and say I wanted to plug in -1, 0, and +1. Well, when I plug -1 in for x, the absolute value of -1 is actually +1. Because again, absolute value makes things positive because distance, which is what it's a measurement of, is always positive. If I plug in 0 for x, the absolute value of 0 is 0. If I plug in 1 for x, the absolute value of 1 would still be +1. Absolute value does not change signs, it just makes things positive. It always gives positive answers. So if I plug these 3 points in, here's a point at 0, 0. Here's a point at 1, 1. Here's a point at -1, 1. Meaning, what we end up getting here, if you continued plugging in more points, what you would end up seeing is we get this V-type shape. Something like that, a V-type shape, which notice in this case is symmetric over the y-axis. Now let's talk about the domain and range for this absolute value function. Remember, domain represents the x's, so we're looking at the x-axis to begin with here, or I should say we're looking for how far left and how far right this graph goes. Well, on the left side, looking at this, I see an arrow here that is pointing left and up, so we are meant to assume that this graph is going to continue going left and up forever. So as far as the domain is concerned, we're just interested in the left part of that, be going left forever, which would be -infinity, much like the linear function did. We also have an arrow over here that is pointing right and up forever. So again, if it's pointing right forever, that would imply that our domain is going to go to +infinity. Now our range is representing our y values, meaning how low does the graph go, how high does the graph go. It's that up and down movement. When we look at this, I do not see any arrows that are pointing down for this absolute value function. So our range will not be -infinity to +infinity. Instead, it looks like the lowest point on this graph is right here at 0, 0. Using the y-coordinate, so the 0 for the y-coordinate, not that it really matters, but just pointing it out, that is where our range is going to start, our lowest point of 0. That is a closed dot, so it should be a bracket, not a parentheses. Now for the top end of our range, certainly we have both of these arrows are pointing up, so whichever one you look at, it's going up forever, or we have to assume it will, so it goes to +infinity. Do recognize your domain will be consistent through all of your absolute value functions. Obviously, the range we have written here is only for this specific parent function. If you start bringing in transformations to change how the absolute value function is shifted, that is going to affect your range. Next, let's take a look at the quadratic function. Quadratic functions have a degree of 2, meaning they have an exponent of 2 on the x. So our parent function would simply be f of x equals x squared. You guys may have seen quadratic functions before and kind of already know that they make a U shape, but the idea would be if we have x squared, remember any negative number squared becomes positive. So for example, if we do an xy table here and we plug in -1 for x, well, -1 squared is +1. If we plug in 0, 0 squared is 0. If we plug in 1, 1 squared is 1. You could plug in -2. -2 squared would give you +4. Alright, +2 squared would give you +4. So you end up with this thing where we have a point at 0, 0 that we would call the vertex. And then we've got the exact same y values on both left and right of the vertex. You have some symmetry here. Along with that, if you plug in enough points, you see that you do not have straight lines, which means we are forced to curve them. And that's where we get this U-type shape. It's not a perfect graph. It should look a little bit more symmetric than that, but you get the idea. It is the same y values on each side. It's just, the x values. Whether you plug in positive or negative x values, you're still getting positive y values. If we want to talk about the domain and range for this graph, What you may notice here, if you take a second to look at it, is that this is going to be this looks very alike to the absolute value function we just graphed. Yes, it makes a U shape rather than a V shape because its slope, its rate of change, is not constant the way it is for absolute value on each side. But we do still have these arrows that are pointing both left and up and right and up. So for our domain, we have to say it is going left and right forever. Or in other words, negative infinity to positive infinity. When we think about our range, you will also notice that this graph does not go down forever. We do have a specific low point right here. It's again the vertex at 0, 0. So our range will start at 0, again with a bracket because it's a closed dot. And then these arrows both are pointing up forever, so we have to say our range is going to positive infinity. It is going up forever. The domain and range for your parent function for a quadratic is the same as your parent function for an absolute value. Also, just like an absolute value, do recognize that quadratic functions will have different ranges when you have transformations. So don't just, memorize that range and act like it's the same for every single one. Let's take a look at the square root function. So as the name would imply, a square root function would be where you square root the input, where you square root x. So the parent function literally is just f of x equals the square root of x. Now, if we want to graph this, just like the others, we'd want to be using an xy table. Especially with this one, I would say we want to be careful with what we choose to plug in. Not that you can't plug in any x values you want, because with any xy table you can always plug in any x values you want to. But we know that sometimes square roots can give us pretty nasty numbers, so we might want to pick carefully to try and pick numbers that won't be terrible to graph out. One thing I would point out is remember that we cannot square root negative numbers. If we do, we get imaginary answers, and those would not show up on the real coordinate plane that we're dealing with here. That's for another lesson. So for now, we just cannot square root negative numbers. No reason to plug those in. That also means we'll be ignoring half the graph, right? Everything to the left of the y-axis is going to be completely blank. We have nothing that we can graph there. Now, 0 is a number that square roots perfectly. The square root of 0 is 0, so that's a good place to start. Then you may want to ask yourself, what's the next number that square roots perfectly, because I don't want to have to deal with decimals? Well, 1 square roots perfectly to 1. 2 and 3 do not square root perfectly, so I don't want to plug them into an xy table. Instead, I'll plug in 4 for x, because I know the square root of 4 is a nice perfect 2. And so if we start to graph this out, you'll have a point here at 0, 0. We've got a point at 1, 1. And then out here at 4, 2. And you'll see again, this is not going to be a straight line. And we end up getting this curved line that is mostly curving right, but is still continuing to go up a little bit as well. Basically, it's like if you took a quadratic and turned it on its side, but had to chop it in half. Which is not really surprising, because if you think about what we are doing, quadratics are where you're squaring, square roots are where you're square rooting, and square rooting and squaring are inverses of each other. So it's not entirely surprising that there is some interplay between the graphs of a square root and a quadratic. The reason why this square root looks like a chopped in half quadratic would be if we did the complete quadratic, this would not be a function, right? If we had the other side of this u that was like that, then this would not pass the vertical line test. So we have to have this feel like it's chopped in half, is basically what I'm saying. Let's talk about the domain and range for this. For the domain, we are trying to figure out how far left this graph goes and how far right this graph goes. Well, the leftmost point is here at 0, 0. It can't possibly go any further left because we already stated we can't plug in negative x values to this equation. So our domain is going to start at 0. Whoops. It is a closed dot, so there should be a bracket. As far as how far right the graph goes, well, we can see from this arrow here, this graph is clearly implying that it's going right forever. So our domain would end
with positive infinity. If we look at the range is how low this graph goes to how high the graph goes. It's actually exactly the same as the domain. This is the lowest point. 0, 0 is the lowest point on the graph. So we are just using the y-coordinate of 0 for the range instead of the x-coordinate of 0 that we used for the domain. And while this arrow is mostly pointing right, it is also going up a little bit. You can see that from the points, right? We start at 0, 0, then we go up to 1, 1, then we go up to 4, 2. It is going to continue going up a little bit each time. So our range also goes to positive infinity. Recognize neither the domain nor the range will be consistent for all square roots. Transformations would immediately be changing both of those if they're left-right, up-down shifts. Last but not least, we've got the cubic function. Cubic, referring to the concept of cubing, meaning your parent function would be f of x equals x cubed, or in other words, x to the third power. Remember that while even exponents like squaring turn negative numbers into positive answers, odd exponents are not the same. A negative number taken to an odd power is simply going to stay negative. For example, if we plug negative 1 into this equation, negative 1 to the third power is still negative 1. 0 is still 0. Positive 1 to the third power would also still be positive 1, meaning signs simply stay the same when you are dealing with an odd power. Negatives taken to an odd power stay negative, positives taken to a negative power stay positive. If we want to plug in a couple more, negative 2 to the third power would be negative 8. Positive 2 to the third power would be positive 8. So if we graph this, we've got a point at 0, 0, 1, 1, negative 1, negative 1, and then 2, 2, 3, 4, 5, 6, 7, 8, all the way up here roughly. 2, 3, 4, 5, 6, 7, 8, all the way down here. And so what we get is this, I guess, kind of sideways S type shape. And what I would point out about this is notice that the graph is continuously increasing from left to right. There's not a change in direction with this parent function, but it does not have a consistent or a constant rate of change, because where you just, depending on which 2 points you pick, will change the slope that you would get if you use slope formula. Okay? If we want to talk about the domain and range for this, what you may notice is that its domain and range is actually very alike to a linear function. I have an arrow down here that's pointing left and down forever, so that covers the beginning of my domain and the beginning of my range. If it goes left forever and down forever, that's both. I also have an arrow up here that is pointing right and up forever, so the right part ends off my domain and the up part ends off my range. Meaning, it is just everything. It's all real numbers. Your domain is from negative infinity to positive infinity, as is your range. And you should be able to pretty much count on that for any cubic function you're dealing with.